So what I'm going to try to do today is try to define intersection number, and then also relate this to if you've heard about this surgical procedure in biological geometry called flips. So let's first start with my goal. Is to define this intersection number between your divisor and a curve on your scheme, projective space, fine space. It doesn't really matter to me. But before we do this, I'm going to make an important assumption: is that everything is Q-cartier, and you'll see why this is an important assumption, and also why this really led to the inspiration of learning or defining flips. So let's have my divisor. Let's have my scheme X and my divisor D, and let's have a curve on this. So I'm just draw this curve like this. Cool. And I'm going to denote these spots as those intersection points. So as you can see, my curve at certain points, so these 2 points is intersecting my divisor transversely, but you see at this point there is some there is going to some multiplicity at this point. So our first kind of way that we would think of in terms of this is trying to actually, given my divisor, I should be able to restrict this to a divisor on my curve. Cool. However, from this, I still want to be able to get a number out of it. And actually, if I was to define the degree of this, it's not necessarily the case that my Cartier's divisors up to equivalence, linear equivalence, is going to be isomorphic to my Picard number. So we're not necessarily able to get a definitive number from this. So instead, what I'm going to actually do is actually normalize our curve. So I've given another again, and this time, just to show the initial picture as well, let's see if I can just move this up. Is that I will now define my divisor again, and my curve. But this time is my normalized curve. Okay, this is the normalized curve. So So as you can see, right, this curve is now smooth, because when we know the normalization procedure, and we know that our singular loci is of codimension 2. So in this case, it's going to be nothing, the empty set. And we can see that hopefully that's actually, when we do try to pull back this divisor on our to our normalized curve, is that we do not lose too much information. That's our main thing. It's not, we don't lose too much information. And this idea of at each point where we get our intersection number with regards to this, because our curve is just going to really focus on where it intersects the divisor, and it also will get some type of ramification from this intersection number. But we don't want it to be too different to what we initially had. That's what I'm trying to portray here. So actually, this normalization procedure I'm going to denote as tau. So this is our normalized curve, C prime. That's our curve. And now I can pull back this divisor. So pull back of D when restricted to C. Cool. And since we now have our curve that is smooth, our Cartier divisors up to linear equivalence is isomorphic to Becquerel number. So now I can define degree. So now I can define my divisor when it intersects with my curve, what number we actually get at as the degree of this. The degree. Okay. So why are we interested in this initially or after all? This is something that, within your first lesson of intersection theory that you probably will come across. However, there's a reason why. So first of all let's get back to that initial part where I actually said that I'm going to assume that everything's Q-Cartier. The reason why we needed that is because for Q, if we assume it's Q-Cartier, then we can pull back these divisors, our divisor D. So let's look at a case where our space or scheme is not Q-factorial, meaning that not all of our divisors are Q-Cartier. They cannot always be pulled back, and we don't really know a definition for that. There are some definitions for wild divisors and pulling them back, but just assume that we don't have that case. We don't have it in general. In the MMP program, what you guys know about this MMP program is that, and again, I'm just going to assume everything is a threefold or higher because of, you'll see why, is that what we want to do is that we have our Mori cone or a closure of a Mori cone, depending on how you define it. And we want to know about all the curves or extremal rays, which are going to be curves up to some numerical equivalence, such that they define some extremal ray on our cone. But I'll just say in general, our curves, let's just say our curves, which negatively intersect our intersect, and we can define this because of Cartier, negatively intersect our canonical divisor Kx. And we want to know what happens because we want to contract these. We want to make our Cartier divisor as positive as possible. So we're going to contract these, or at least as non-negative as possible. But there are some cases actually when we do contract these, we end up in a very, very strange place. And this is when we have a small contraction. And this is when no divisor is contracted in this birational morphism from pi, and this is when our let's just say some extremal ray is contracted from our x to this space z, this schemal space z. So why is this a strange case? Why is this a strange? Why do we need to pay attention when we have these small contractions? Like I said, there is no divisor that's being contracted. So actually, with this, let's assume things are Q-Cartier. Z is Q-Cartier. So let's say it was Q-Cartier for baseline assumption, and let's see what happens. Well, when I pull back, let's just say it's Q factorial, sorry, Q factorial, and everything's Q quartier. When I pull back my canonical divisor of Z, again, because no divisors have been contracted, and we don't really need to think about too much ramification. This is going to be our Cartier divisor of X. Our Cartier divisor of X. Again, it's because we know much about our map. We just know everything that's been contracted is codimension 2 or greater. And let's say one of our curves that we have contracted, let's try to intersect it with our divisor. So this is one of our curves that we've contracted, CI and CI. Well, let's look at this right hand side. Well, this right hand side, I can now use this projection formula. And actually, because, again, our assumption that is contracted, this right-hand side becomes 0. But we started off with this idea that we're contracting these extreme arrays, these curves which are negative on our canonical divisor. So our left-hand side is actually less than 0. So we get a contradiction. And this is telling us that actually when we actually contract or have these small contractions, is that in some of these cases actually is that where no divisor has been contracted and we have some birational morphism, is that our space on the other side has actually become too singular, and we can't even define all of our divisors to be Q Cartier. So the remedy of this situation was our initial topic that we want to describe is actually flips. So we start with X. I'm not going to define a flip. Maybe I'll do it in a future lesson. And down to Z. R space Z. And the idea is that X plus is still, with some other terms which actually make it much better than what we start off with Z, is that X is actually Q Cartier, Q factorial. Q factorial. So this is our reason for us realizing that intersection number, Q Cartier, Q factorial, all play a central role with regards to understanding MMP, and also understanding the intuition behind what we'll define as a flip. Okay, thank you. That's not the recording.